Good evening, everybody. I'm excited about presenting this to you guys tonight because a lot of you diehard Michael Penn channel subscribers were involved and very interactive with this very interesting problem about 2 to the 29th, where it was stated that it was a 9-digit number composed of distinct digits with a missing digit. And at first, I didn't get it at all. I go, what? It's like, what, he used a calculator? I finally got it. It says that's the whole point. He's using that as a given. That's just information that's being given, and we use other mathematical tools to discern or infer which of the digits is missing. Now, the digits are 0, 1, 2, 3, 4, all the way through 9, right? And so if all 9 were present, that would sum to 45. So it turns out mod 45 is quite important here. But I'm going to state a few facts here. One is that over and over we were beat down with this, but it definitely is a useful truth, is that any number is congruent to the sum of its digits mod 9. And really 10 to the n congruent to 1 is why it's true. You just use that, string that together, and you can see why it falls out. You're replacing all the powers of 10 with just 1, right? And so that just leaves the digits in the sum of the digits. Now, this is also true for mod 3, but there's only 3 remainders going on there. So it's a little hard to use. I think it would be ambiguous. There's only 3 remainders, mod 3, namely 0, 1, and 2. So that might point to more than one missing digit. Well, it would in the case the digit was 3 or 9, right? But in any event, we use mod 9 for a very good reason. And then this distinctness condition implies this statement right here. Now, 22 to the 29th is congruent to 45 minus d, where d is the missing digit. Simple example, if 0 is the missing digit, well then that would be congruent to 0. 45 is divisible by 9, right? And if d were 1, the sum of the digits would be 44. All right, so if you get 2 to the 29th congruent to 44, for example, you would know that the missing digit was 1. Now let's get into it, because the way Dr. Penn did it was he used the totient function, which was met with some controversy. Many subscribers and commenters on the YouTube channel said it was unnecessary. And one guy did it just completely congruentially, starting with 8 congruent to -1. And then another guy was who opens all his comments with "I have a better way" or "I have a more efficient solution," said he did it with the binomial expansion. And I thought he was sounding off pretty hard about it, like it's just trivial, it's easier. And I thought, well, he's the dog that's barking the loudest. Let's check it out, And sure enough, he's exactly right. I went ahead and my approach on this video was to do the binomial expansion. So 2 is easily equal to 3 minus 1. You guys can recognize this binomial expansion with the binomial coefficients in combination form. 29 choose 1, 29 choose 2. All of those are numbers that are divisible by 29. And I thought that's what he was getting at. But it turns out to be inconsequential that all these terms are divisible by 29. The key thing to observe here, and the first thing to observe, is there are exactly 28 terms that are divisible by 3. Starting at 0 right here, all right, certainly 3 to the 29th is divisible by 3, but if you look 0, 1, 2, all the way out to right here, 3 squared, that's 28 terms, okay, starting from 0 and going to 27. That's 28 terms. All 28 of those terms in the 30-term expansion are divisible by 9, okay? In other words, another way of putting that is the sum of those first 8 terms is congruent to 0 modulo 9. Now that's huge. I mean, that is huge. Now what's left over here that's not divisible by 9? Well, it's 87 minus 1, it turns out, which is 86. Okay? So what we get right here is that this congruence, 86, it's all that's left after you get rid of the mod 0, 9 terms. And so you get 2 to the 29th is congruent to 86. And again, y'all, the 86 comes from these 2 terms. Those are the only 2 terms that are not divisible by 9, okay? And so that's pretty awesome. 28 of those terms just got wiped out by the binomial expansion, and you started at 86. Now, if you remember in Dr. Penn's, when he used totient, I think we started at 32 and also showed that it was congruent to 41. Notice that 32 and 86 are part of the same equivalence class. 86 minus 32 is 54, which is a multiple of 9. But so it proves that the way Charlie Common did this thing is it's completely different. It got a different member of the same equivalence class. And in that sense, it's similar, but the binomial theorem started us at 86, right? Which reduces back down to 41 modulo 9, just like 32 did, right? But what's special about 41? Well, it's 45 minus 4, right? And that go back to this fact. And so you get that 4 has to be the missing digit, all right? So again, my hat's off to Charlie on this one. Most math people have some degree of hubris. We wouldn't be math people if we didn't. We're confident in our abilities. He's very confident, but I do listen to him, when he speaks or comments, because he doesn't just sound off for the heck of it. He's usually right, and this is no exception. It didn't occur to me to try the binomial expansion. Okay, now let's move down here just a little bit. Now I just wanted to go ahead and kind of summarize just. Being on this channel of Dr. Penn, just this video alone created its own universe and soap opera, right? This gentleman here, Doug Rosengard, figured out a way to do it just by starting with A congruent to -1 mod 9. And then it was completely congruential. He did manipulated this thing. Notice that this is the same as 64 to congruent to 1, which is what the totient function gives. If you square both sides, you get 64 congruent to 1 mod 9. Which is exactly what the totient function produces for us. And then, like when Charlie's saying his way is more efficient, I tend to agree with him. The binomial theorem gets you right into a very easy congruence to solve. And so in some sense, I guess the binomial theorem is a little better. It doesn't depend on maybe a more obscure result. Totient's well known in number theory, and I wouldn't call it obscure. But there are many of the commenters said, hey, I can just do this without knowing what the totient function is. And they're right. The binomial theorem does it, or this way does it. So again, I hope you guys enjoy the video. I had a great time on this thing. It was so much fun. It's so much fun in the college math classes where everybody's just trying to get the assignment done. Everybody loves what they're doing here, and it creates a lot of good interactions which produce unique and different solutions. Good night.